So in this tutorial, we are going to revisit conservation of energy and angular momentum from an angular standpoint. We're going to see that it's very similar to what we've learned before, except that there is a R component and some of them are angular components. I'm going to start off with a familiar problem, a marble or a sphere rolling down a ramp, and look at it from an energy standpoint. Once we're done with the energy, then we're going to take a look at momentum again and see how far we get in the 15 minutes we have here. Okay, so again, we have a sphere on a ramp, and ultimately, let's say we want to find the final velocity at the bottom. Okay, so if we take the second law approach, we've already done the derivation the other day, where we found that the acceleration down the ramp, because of the combination of a torque due to the force of friction and a linear acceleration due to the parallel component of the force minus the force of friction, we got an equation that said the acceleration was 5/7 g sine theta. Okay, which was a fraction of what we'd expect if it just slid down the ramp. And if we want to solve for the final speed, we know from kinematics that v squared equals the initial squared, which is 0, times acceleration, twice the acceleration times the distance. Okay, so we substitute in and take the square root. We have v at the end is equal to radical 2 times 5/7, which is 10/7 g sine theta times d. Okay, so that's all well and good, but if we were to have a different shape, and solving for A again is a kind of a pain in the butt. It's long and tedious, and on top of that, if our ramp wasn't straight but curved, then we really couldn't use the second law approach, at least not easily. So we've learned also that it's much easier to approach this from a conservation of energy standpoint when we know the height that it's going to fall. So let's address that. The only twist to the familiar problem of calculating potential to kinetic is that because the marble is rolling, it's going to have another type of kinetic energy, and that's rotational kinetic energy. So we want to take that into account, solve for how, or determine how to calculate that and fit it in with the regular kinetic energy. So it's not too bad. The derivation may seem a little long, but it's pretty straightforward. Okay, so let's go with what we're familiar with. At the top, the marble has potential energy, and we know that's mgh. And at the bottom, it's going to be converted. We're going to assume no thermal losses. Even though there's friction, the thermal losses will be minimal. So it's going to be converted to kinetic energy. I'm just going to keep that as Ke, and then a rotational component, which I'll call KER. All right, so we got to recognize now when something is spinning or rolling, it has to have a rotational part of its kinetic energy, even if it's not going anywhere. All right, so how do we calculate the kinetic rotational kinetic energy? So let's start with what we're familiar with. Let's just look at kinetic energy itself, Ke, not the change. I'll just look at that. So we know that's 1/2 mv squared. All right, so I want to take out the v and put in the rotational part because it has a rotational velocity. So we know that v equals omega r. So if I substitute that in, I have kinetic energy, rotational now, is going to be equal 1/2 m omega r quantity squared. And I could stop there. That is technically correct, but this can be simplified. So if we expand that out, I have 1/2 m r squared times omega squared. And if you look at this closely, hopefully you recognize that mr squared is nothing more than, that's correct, the general equation for rotational inertia or moment of inertia. So if I substitute that in, I have a nice simple equation for rotational kinetic energy, which is 1/2 I omega squared, where omega again is v over r. So we have a kinetic energy that looks very similar to 1/2 mv squared. I is the angular component of m, and omega is the angular component of v. So that shouldn't be too hard to remember. So now let's put it all together for our problem. At the top of the hill, we have gravitational potential, which is mgh. At the bottom, we have linear kinetic and some rotational kinetic. Alrighty, so given the information, the mass of the marble, the angle, the height, etc., we have to basically substitute out the moment of inertia and the angular velocity. So that's not too hard. We know that the moment of inertia, because it's a solid sphere, is 2/5 mr squared. Leave that as lowercase. And we know that omega is equal to v over r. So let's substitute in and see how it simplifies. So we have mgh equals 1/2 mv squared plus 1/2 2/5 mr squared times v over r quantity squared. All right, so let's tackle this mess on the second term. And first of all, let's make it always a little bit easier. Cancel out the m's. Okay, so we have GH equals 1/2 v squared plus, okay, we have 1/2 times 2/5, so that's 1/5. R squared and the R squared cancel out, and we have v squared. Oh, that's nice. That's really nice, because this is going to simplify pretty well. Let's make sure I didn't make any silly mistakes there. I think I'm good. Okay, so this becomes, let me add the two terms on the right. So we have GH equals, let's see, 1/2 plus 1/5. Common denominator is 10. 5/10 plus 2/10 is 7/10. Hey, look at that. 7/10 v squared. And we solve for v. And we get, bring the 10/7 over there, GH, radical GH. Look at that. Okay, and if you look up above what we had before, we had radical 10/7 g sine theta d, but sine theta of d is nothing more than h. All right, and if you recall when we did a problem a long time ago where an object slides down, the equation for final velocity is radical 2gh. So this is not quite 2gh. We see it's a little less than that because the bit of our energy is rotational. And notice again that the velocity does not depend on, okay, mass. We know that. Okay. Nor does it depend on the size, the radius. Okay. But instead, it depends on, more than anything, the shape that's rolling, and of course the height that it drops. So we can do the same problem with a hoop that is falling. Okay, and it's the same type of idea. Okay, so so we have to go through this again. Do I want to go through this again right now? No. I'll let you try this one. Try this yourself. Okay. Okay, just I'll help you out a little bit. The hoop's rotational inertia is mr squared. Okay, so I think it's a good exercise for you to go ahead and solve it. I'll give you the answer in a second. Okay, so you can plug in numbers, but if you go through the process again, you should find about the speed at the bottom is radical GH. Noticeably less than for a sphere or for something sliding, because a hoop is the shape that generally has the greatest rotational inertia when we're talking about rolling. All right, so that's just a review or an introduction to rotational kinetic energy. Everything else in terms of conservation of energy holds. We just now got to be aware that something rotating has a rotational kinetic energy. All right, now let's turn our attention to momentum. Okay, so I don't think it'll come to a shock to you, but there is an angular component to linear momentum, and it's called angular momentum. And angular momentum is actually very, very important in many, many problems. Just as important as linear momentum. We just don't think about it much. And the symbol is capital L. So let's relate angular momentum to linear momentum. It's pretty straightforward, but there's a little bit of subtlety to it. So angular momentum is equal to linear momentum P cross R. Okay, so it's like torque is F cross R. We see that angular momentum is momentum cross R. So it's cross product. We're looking for the part of the linear momentum that is perpendicular to our angle or our axis of rotation in a certain distance away. So let me put that again. So again, it's a component of your linear momentum multiplied by the distance from where that object is to the pivot point in the perpendicular line. In other words, a lever arm. Okay, so we can express it two ways from this general idea. We know that linear momentum is mv, so that's going to be mv cross r. So one way of saying L is that it's mv cross r, which really translates to mvr sine theta, whatever the lever arm is, that angle. Okay, so it's very similar to torque. Now we can tweak this a little bit more. Okay, so we're going to assume that a perpendicular, so theta is 90, so this is just mvr, and we know that v is omega r times r, so we have m omega r squared. Well, mr squared, again, is moment of inertia. So another way of expressing angular momentum is I times omega, which kind of makes sense. mv would be what we have for linear momentum, so I omega would be for angular momentum. And lastly, we can write the second law of motion in terms of angular momentum. In the linear, we used to be able to say F equals ma, or F equals the rate of change of momentum. That's actually the more general way of doing it. So we can do the same thing here. Instead of F, we can say tau is equal to the rate of change of angular momentum. Okay, next. Perhaps most importantly, angular momentum is a conserved quantity when there are, that's correct, no external, not forces, but torques. Okay, so put this way, when something is rotating, it wants to keep rotating, and it has a certain angular momentum. And if you drop things on us, let's say a spinning table, that's not changing or not introducing external torque, so the angular momentum will stay the same, but the moment of inertia will change because of the added mass and where the mass is placed, and therefore the object may start spinning faster or slower. So there's a lot of common applications of that. The classic one is the ice skater who is spinning around. Okay, if she is spinning around with her arms wide out, she has a certain moment and a certain angular velocity. If she brings her arm in, there's no external torque on her, so her moment will drop, so her angular velocity will have to go up, and it can go up quite dramatically. So mathematically, we can say sigma L equals sigma L prime. In sigma L, generally we're just talking about one system, not necessarily two objects that are colliding like we usually associate with angular momentum. In linear, we could say I omega, that's the angular momentum of an object, equals I prime omega prime. Okay, so we have a few minutes. Let me do one or two problems here just to give you a flavor of angular momentum before doing class. So the first one I'm going to do is probably the least obvious. Okay, so we have a ball that rolls along the floor on the forward, and it's about to collide with the stick, and the meter stick can pivot about this point right here. Okay, so it's not really free. Well, let's say there's no friction, so it's not on a pivot point, but the center of mass is what it would do. All right, so I'm going to ask, what is the angular momentum before the collision for the following systems, right? If the system is just the meter stick, well, it has a moment of inertia, so we're going to basically look at that as I times omega, but it's not rotating, so the L of the stick is simply 0, okay? That's pretty easy. But what if we include the ball with the system? Okay, now you say, well, forget about the fact that the ball is rolling. Okay, we could just as well say it's sliding across the floor. That doesn't really matter. Is there any angular momentum relative to the stick? And the answer is actually yes. Okay, even though neither are spinning around, because this guy has a momentum forward and is acting a distance away from the pivot point. That's r, or half the length of the stick. So what we can say for the system is that L equals the momentum of the ball across the lever arm of the stick, okay? Or we can say it's equal to mv times r. And so that's an easy thing to overlook. Now if we put in the numbers, we have 0.4, we have a speed of 2 meters per second, and an r of, well, it's a meter stick, so 0.5 meters. Okay, so let's see, 2 times 0.4 is 0.8, 0.8 times 0.5, I think is 0.4. All right, and what would the units be? We have kilograms, meters per second, times meters, so kilograms, meters squared per second. So odd units for angular momentum. All right, let's do one more. Try to do this one quickly, and then we'll talk about the last one in class. So we got a classic diving problem where a diver is spinning around with a large I, or a small I and a large W, and then they come out into a tuck. And we want to know what's the angular speed when they're in a straight position. Okay, so we want to recognize as this person is rotating about a certain axis, all right, when they change their body shape, they're not introducing an external torque because your body can't put a torque on itself in a sense. So we can say that sigma L equals sigma L prime. All right, and how do we get the first one? Well, that's just I omega. That's going to equal I prime omega prime So if we're looking for omega prime, when they come out of it, omega prime is nothing more than the original moment divided by the final moment times the original